Welcome back to Izzo Math. Today we're going to talk about inverse trigonometric identities. Note, e to the I pi plus 1 is 0. You will figure that out in Calc 2, okay? Anyway, what we're here today for is the inverse trigonometric identities in your text, and we're actually only going to talk about really one aspect of the identities that we find more useful in the calculus series. So let's jump to it. Let me just use a simple example here. Let's say f of x, well, let me not even call it f of x. Let's just say cosine of pi over 2, cosine of pi over 2 equals cosine of pi over 2. Draw a circle at pi over 2. We're up there, so my cosine is 0. Okay, so we know the inverse cosine of pi over 2 equals, remember, the inverse cosine takes the outputs and sends them back home, takes 0, sends it back to pi over 2. Okay? So, now if we look at this, the cosine, let me go on a different color here. So the cosine of the inverse cosine of 0, what's that going to equal? Well, we should remember from inverse functions a long time ago that the composition of f composed with f inverse of x yields the identity function. That is, when you stick something in there, it spits it back out. So this should be 0, but let's make sure. So the cosine, if we look at the inverse cosine of 0, we get pi over 2, and the cosine of pi over 2 equals 0. Okay? So when we compose the inverse functions, we get the identity function. The only tricky part is, in some of your homework problems, you'll have something like the cosine. Let's talk about the cosine of the inverse cosine. Well, no. Let's go the other way. So let's say the inverse cosine of the cosine of, and let's go with 1, 2, 3, 4, 5 pi over 2. Well, you might be tempted to say that that equals 5 pi over 2, but that is going to be wrong. The range of the cosine, so the range of the inverse cosine, or the inverse cosine is going to go from here, so the range is 0 to pi, and 5 pi over 2 is not in there, so you'd have to break this one down to see what it is. So it's going to be the inverse cosine of 5 pi over 2. Here's 1 pi over 2, 2, 3, 4, 5. So cosine is going to be 0. And so it's going to be the same as the one up there. The inverse cosine of 0 equals 0. So you have to be careful and make sure when the cosine is inside there that output is still within the range of the inverse function if it's going to yield the identity function. Okay, let's do another one. Let's look at the sine. Am I looking good? So the sine of, I don't know, negative pi over 4 equals root 2 over 2. Okay, that means that the inverse sine of root 2 over 2 equals negative pi over 4, because the inverse function just takes It takes the outputs, sends them back home. Okay? So we'll see here that the inverse sine, when we compose these functions, the inverse sine of negative pi over 4. Now, is it negative pi over 4? That is, can that be the answer? So is negative pi over 4 in the range of the sine? So, quickly here, drawing a sloppy circle. That's too sloppy. So that's not much better, but let's go with it. Okay, so the inverse sine is over here on this arc. Okay, from negative pi over 2 to pi over 2 are going to be the outputs. So does negative pi over 4 lie on that? So yes, it does. So that would be the correct answer. So let's give an example where it might be a little more confusing. So the inverse sine of the sine of, and let's stay at that same angle, but really let's call it 7 pi over 4. I mean that puts us with the same radius of the unit circle. And if you put 7 pi over 4 for that, it's going to be incorrect, because it's an output of the inverse sine, and the range of the inverse sine is going to be from negative pi over 2 to pi over 2. So you got to think about these a little bit. And again here, just to, so the inverse, or so the sine of the inverse sine of the inverse sine of root 2 over 2. Okay, now if you think about it, this spits out the angle that gives me a sine of root 2 over 2. Well, then you turn around and you plug it into the sine function. So it equals root 2 over 2. And when we have the inverse embedded inside the regular function, we're never going to have any issues. It is always going to be the identity function. But when the function itself is embedded inside the inverse, you have to really check and make sure that that thing is in the output of sine. So I think we have time for a tangent. Yes. So let's say we have the tangent of let's go with pi over 6. Let's go with pi over 3. Pi over 3. So on my unit circle, okay, and we know that when we're dealing with the inverse function, we're on this arc over here, and so the tangent of pi over 3 is going to be, so pi over 3 is there, so that's my big one, that is root 3. Tangent of pi over 3 is going to equal to root 3, and that would mean that the inverse tangent of root 3 is going to equal to, well, again, the inverse function takes the output root 3, sends it back home, equals pi over 3. So if we look at the tangent of the inverse tangent of root 3, so the inverse tangent of root 3 gives me an angle such that its tangent is root 3. Well, then you plug it into the tangent, so that equals root 3. So if we do the inverse tangent of the tangent of pi over 3, so the tangent of pi over 3 gives me root 3. Well, so then the inverse says what angle gives me a tangent of pi over 3 or root 3. So that's going to be pi over 3. That is, you put pi over 3 in, let's get pi over 3 out into this composition. Okay. Again, the only issue would be, say we had the inverse tangent of let's say 1 power 3 and add 2 pi. Let's go to the, let's just say 2 pi plus power 3. Okay, so that is not going to equal to 2 pi plus pi over 3, because the output of the inverse is between negative power 2 and power 2. So you would have to forget about the 2 pi here and to realize that that is power 3. Okay? So I'm going to leave it at that and go assign you ladies and gents some homework. Okay? See you next week.